So I think recording has started.
Yes, sir. Yes.
The screen visible.
Yes, sir. No, screen not visible.
Let me connect to this. It is coming black or something. Or
It is, sir. It is showing video. Only your face is visible.
oh, okay. I have actually forgot to share my screen. Okay, is now it visible?
Yes, yes. Now it is visible. Applied dynamics, kinetic energy.
Okay. So, minute. Okay. So in previous lecture, we derived the equation or motion of pendulum using maximal coordinates. That is whatever variables were there. We took them all and we derived the equations of motion using DAE method, and then we solved it using numerical technique with the help of MATLAB. So now, in order to solve more complex systems, we need a little more tools. So for that, we will be today we will be discussing about the kinetic energy of the system of particles. In previous lectures, we defined the angular and linear momentum of the system of particles. So in today's lecture, we will first define the kinetic energy of the system, and then we will discuss Lagrangian approach of solving the problem. And finally, if time permits, we will discuss the rotation rotation of 2D body, rigid body. Okay, so this is the this is the system which contains n number of particles having mass m1, m2 up to mn. And each of the particle, like if we take m1, it is moving with v1 velocity. And if we take m2, it is moving with v2 velocity, so on. And mn is moving with vn velocity. Now we know that the kinetic energy associated with the particle is nothing but half times mass of the particle times the magnitude of velocity square. So this is the definition of the kinetic energy associated with the particle. Where this more to be more specific, it is the second norm of the velocity vector. So let me try to explain what I am trying to say. Okay, so if we have a vector, is this whiteboard visible to you?
Sir, whiteboard is visible, but your cursor is not moving. Now it is moving. Can you write something, sir?
Oh, problem has occurred. And the problem is that since I have not downloaded the extension file for this pad, that is Wacom. I think, okay, but let me use cursor, my mouse to draw something. Okay.
Yes, yes. Now it is written something on board.
Okay, so let this be some vector. Okay, obviously it will have uh, some Vx, Vy, and Vz. It will have three components: Vx, Vy, and Vz. So we define the norm of the vector like if we take the first norm, uh, this is known as the first norm. This is defined as Vx, okay, plus Vy plus Vz. Then we define the second norm like this. And this is nothing but Vx square plus Vy square plus Vz square. So this is known as the second. So, but here, when I am saying the mod, like you can see, when I am saying mod of V, so it is not the first norm, it is the second norm. Okay, so it is basically this one, the second one. Although I have put only one like this, but you should understand that it is not the first term, it is the second. Okay. So the kinetic energy is nothing but half m second norm of velocity square. We can write this second norm as v dot v. So if you see the second norm is nothing but vx square plus vy square plus vz square. I can write this v as vxi plus vyj plus vzk. Okay. So now when I take the dot product, so if I take the dot product of that is v dot v, so taking the dot product, that is v dot v, so it is basically the dot product of these two, which is nothing but vx square plus vy square plus vz square. Okay, and this is nothing, you can see it is mod of v square. That is second norm of v square. You take this, square this on both sides, you get this is nothing but square of this. So That is what I have written here. So basically Ek is equal to 1 by 2 mv square can be written as 1 by 2 m v dot v. So this is the kinetic energy associated with the any particle having mass m, point particle. But here we are looking, so if this is the mass m and it is moving with v, this is the kinetic energy associated. But we are looking to the kinetic energy associated with a system of particles. Okay. So how we will define it? So we define the kinetic energy of the system as E sub k. And by definition, this is by definition, the symbol for by definition. And it is equal to 1 by 2 m1v1 square. That is the kinetic energy of this particle plus kinetic energy of second plus kinetic energy of third up to kinetic energy of nth particle. So this is the kinetic energy of the system. So I can write it in the condensed form as summation of 1 by 2 mivi, where I will run from 1 to n. So if I run I from 1 to n, I will get this summation. So this is the kinetic energy of the system. Now, where this vi is nothing but vi, a mod of vi. Okay, so uh, is it clear until this?
Yes, sir. Yes, sir.
Okay, if you have a question in between on confusion, let me know because I will feel like you are getting everything. So Vi is nothing but the velocity of ith particle, and Vi without any arrow on top, it is the magnitude, second norm of the vector. Also, we have previously seen that we can write Vi equal to Vg plus Vig. So I have shown this previously, but let me do it again. So what I am saying is that if we have, this is some ith particle, and this is the center of mass associated with some systems. There is some system. I am taking some ith particle among this system, and I am considering the center of mass for the system, which is G. By geometry, you may say that how can G be here, but I have drawn it like this. And maybe more particles are on this side, so G is here. Let's assume G is here. So this is Vg. So this is Rg. And similarly, we can see this is Ri. And this is nothing but Ri with respect to G. So I can write the expression as Ri is nothing but Rg plus Ri with respect to G.
Yes,
So
sir.
you differentiate this expression on both sides, you will get Vi, and this will be Vg, and this will be Vig. Okay, this is so simple. Nothing new here. So we can write this Vi, that is the velocity of ith particle, as like as this. And we have expression for kinetic energy here. So let us substitute this this Vi in this expression and write this Vi square as Vi dot and Vi dot. So for Vi, we write this Vg plus Vi with respect to G. So this becomes the dot product of these two. Okay, summation is there. And now let us expand this expression. That is, we will multiply this Vg with this Vg and Vig with this, similarly this and this. So you know, if we have A plus B dot C plus D, it is equal to A dot C plus A dot D plus B dot C plus B dot D. Okay, So similarly, we will expand this expression and we get v dot g dot v dot g. Okay, multiplying this and this plus this plus this. Okay. So what is vg dot vg? It is the second norm of this vector, that is vg, or the magnitude of this vg vector. Okay. Similarly, uh, this I have taken this expression and I have multiplied it with each of these terms. Okay, so this is 1/2 summation of mi. This 1/2 summation of this. Okay, summation of mi twice vg plus similarly for this expression. Okay, but we know that Rg by definition, that is the position vector of the center of mass, is nothing but summation of mi Ri upon summation of mi. Okay, so multiplying this, we get this. Okay, differentiate this expression. When we differentiate this expression on both sides, we get summation of mi. See, this Rg is constant. It does not depend upon which particle you are taking. It is something which is characteristic of the which is constant for this system. And if you run I from 1 to n, this Rg will not change. Okay, it changes with time. I'm not saying that, but when you are summation with respect, summation running from first particle to the nth particle, this doesn't change. Okay, this is some fixed point at a given instant of time, irrespective of which index you are using. So this RG is outside this summation. Okay, this summation is only for this M. So when you differentiate this, and since mass is not changing with respect to time, so you can only put the derivative for this RG. So that is d by dt of RG. Similarly, on this side, it will become Mi. Mi is constant d Ri upon dt. See, this whole is inside the summation because Ri depends upon the ith index. For example, R1 is different from R2, which is different from R3. So this is not outside the summation. This whole is inside the summation. Is this clear?
Yes, sir.
So d by dt of Rg is nothing but the velocity of center of mass, which I have written as Vg, and mi. D by dt of Ri is nothing but Vi. Again, I can write this Vi from this expression
Vi plus
as
VGR.
Vg. Okay. So that is, I have written this Vi with respect to G plus Vg. Okay. So this summation of mi Vg is nothing but mi Vi with respect to G, summation of mi Vg. Now, you can see that mi Vi with respect to G is equal to 0. I think we have proved it before, but from here you can also see that if you see this term and this term, these are similar, so they cancel out, and the only term which remains here is the summation of mi Vi with respect to G, and that is equal to 0. Okay, so we have got this term, that is mi Vi with respect to G, summation of this thing is 0. So coming back to this expression, so this summation of mi Vi with respect to G, you can take this Vg out because Vg is constant
Constant.
from this summation. 2 and 2 will cancel, so there is summation of mi Vig. So this term cancel out, it is 0. Only
That-
term left out is this one and this one. That is what I am writing here. Ek is 1 by this plus 0 plus this. So we have got some bigger picture of the kinetic energy. So kinetic energy of the system is nothing but the summation of the kinetic energy of each of the particle. And that comes out to be equal to half of total mass of the system and velocity of the center of mass square. So it is something like kinetic energy of the center of mass. So maybe initially you would have guessed that the kinetic energy of the system is nothing but the kinetic energy of the
the mass.
center of mass. but something else is also there. See,
Yes.
we have this thing that is kinetic energy about the center of mass. Okay, so the total and kinetic energy of the system is not only the kinetic energy of the center of mass, but also the kinetic energy of the about the center of mass. So these are the relative velocities with respect to the center of mass. So this is something which we can call as the kinetic energy about the center of mass. This is by definition. I am saying that this is the definition of kinetic energy about the center of mass. Okay. So we can have a system which is not moving. That is, its center of mass doesn't move. Still, it will have kinetic energy, maybe due to randomness. Assume that we have a gas, and the gas particles are colliding with each other. They are repelling out, but the gas is inside the container, so we can say its center of mass does not move because it is confined to that container only. Okay. So we can say that the kinetic energy of the that this term is zero because Vg is not moving, but this term is there. And obviously the gas has energy, which sustains, that is, if the gas doesn't have energy, it will not sustain in the gaseous form. And that energy is contributed to this term. Okay. So now the big picture which you will keep in mind is that the kinetic energy of a system of particles is nothing but the kinetic energy of the center of mass plus the kinetic energy about the center of mass. Okay. So now we have, if we have a point mass, say m, and it is moving with v velocity and f force is acting on this mass particle, we know that the small amount of work done in dt time is nothing but f dot v. Okay, so but we also know from what is that known as? I think work energy theorem that the change in that the work done is nothing but the change in the kinetic energy, or the work done on the system is the change in the kinetic energy of that system of the particle. Okay, so
Okay.
yeah, any question?
No, no, sir.
Okay, so now this dw is nothing but
F
from
dot T.
this it is f dot t into dt, and this is d into k, that is change in the kinetic energy. And f dot v is d by dt of kinetic energy. So see, F is the force acting on the particle, V is the velocity of the particle, K is the kinetic energy of the particle. And this is the expression which connects the kinetic energy, force, and the velocity. So what
Okay.
about the
System of
system which contains n number of particles? What what is there any relation like this? For example, we have a system and F external is the net external force acting on the system. And if we dot it with the velocity of the center of mass, what is this equal to? We want. So maybe your guess. So let me take your guess. So what do you think? F external dot Vg. What? According to this, for example, if we have some particle, it is
sir,
is
it would be F external dot Vg is equal to d by
mhm,
dt of one
mhm.
half of m total into v velocity of center of mass plus d by dt of summation of miv square.
Okay, hold on. I will write. Okay, so you are saying F external dot
Vg square. Vg
Vg
is equal to.
is equal to d by dt of
Now, sir,
what?
replace the yes, sir. Now replace the kinetic energy with
Hmm.
the term that we prove above. That is one half
1
of
by 1/2 of m
total.
total Vg square
Yes, sir.
plus
summation
summation
of
of
mi
mi
vi square.
vi with respect to g.
Okay.
So you think it should come like this?
Yes, sir.
Yeah.
Yes,
Okay.
sir. And mt and vg is 0.
Uh,
D by dt of mt and vg is 0.
what?
No, 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 so sorry, not vg is 0.
So it is not always that Vg will be constant.
Yes,
Maybe a system as a whole is moving, so
yes.
Vg will be moving.
Okay,
Okay,
okay.
for example, we have a rod. Let
Yes.
us think we have a rod, massless rod, and it has M1 here, and say it has M2 here. Okay, and let's assume that this rod goes like this. So center of mass is here and it follows this trajectory. So obviously the
Yeah,
velocity of the center of
change-
mass is
changing.
changing. Okay, so your first guess is that this F external acting on the system should have the relation like this. The second question might come, what is the d by dt of Ek itself? Okay,
I think so. It is power.
yeah, I don't know what English terms you are using. I just want the
The
mathematical
power,
expression.
sir. Not that part is power. F into v is power of the system.
Yeah,
Detailed by dt.
yeah, you are correct in the sense that if we look at this thing, where is this? F dot V. This is d
Yes,
by
sir.
dt of kinetic energy, and the rate of change of the kinetic energy is nothing but the power. Okay, so F dot V is power. Yes, it is fine. But I am saying, what is this d by dt of Ek? How you will be relating it like with the total mass, external forces, or maybe something related to the central mass. So how we will get that picture? Okay, these are some of the questions which should come to your mind after solving, after having the expressions for the point particle. What are the corresponding relations with the n number of particles? Okay, these are some of the questions. Like also you should be thinking what will be the d by dt of, what is this? 1 by 2 summation of MIVS square. This is same as this. These are not different. You should now be able to guess. This is the total energy of the system, and this is also the total kinetic, I mean kinetic energy of the system. These two are same. Okay, when I am calculating the kinetic energy, I am assuming that there is no interaction between the particles. So there is no potential energy. Okay, I am just looking these n number of particles as the non-interacting. There is no gravitation, there is no attraction, repulsion, nothing is there. They are individual particles, and I am just looking what, although they may be interacting, the expressions will be same. There is nothing to worry, but okay, we can generalize it. Maybe the particles are interacting, but this expression will not change. These are the kinetic energy only which I am concerned about. Okay, so this is also the kinetic energy of the system, and we want some expression for this. And the obvious question is, what is this d by dt of the kinetic energy of the center of mass? Is what is this equal to? Okay, so let us take this d by dt of this thing and let us differentiate it. Okay, let us take this expression. That is the change, the rate of change of the kinetic energy of the. This is not square here.
Yes, sir.
This is the mistake here. Okay, maybe I can draw it. No, draw it. So this is not there. Okay. Uh, So the d by dt of this thing is d by dt of half, and this is summation of mi. Again, taking the dot product of these two, and this is nothing but rg dot by definition. Okay, 1/2 of summation of. Now I can write this rg dot as summation of mi ri dot divided by summation of mi, and this is by definition. This is by definition of center of mass. So uh, you have this Rg. This is equal to summation of Mi Ri
Divided by
upon summation of Mi. Okay. Similarly, if you take the dot here, you will get dot here. So that is what I have replaced this Rg dot by summation of Mi Ri dot upon summation of Mi. Similarly
yes.
for this. Now you can cancel these two. So we will get d by dt of half summation of mi dot summation of mi dot upon m total, because there will be this summation of mi, which is nothing but total mass of the system. Now you can differentiate this thing. You will get what? Okay. Take this m total outside this and 2 outside, and now we have d by dt of this thing and this thing. Okay, summation of the summation of MIRI dot MIR. Okay, so now let us go to whiteboard. Today I am not feeling good at writing on the whiteboard because I have to write with the cursor. I have to download the extension for this pad. Okay. So if we have a vector v, we have a vector v dot, we have another vector v, and we want to differentiate it. So what we apply? We apply the chain rule. That is, okay, let me generalize it. Let this be v1 and this be v2. So what we can do is take the derivative of first vector. This is not the chain rule, this is the product rule. v1 dot derivative of second vector, that is v2 dot. v2 dot plus derivative of first vector dot second vector. So now when v1 and v2 are equal to, so this will become v1 dot v1 dot, and this will become v1 dot v1 vector. Okay, so since this dot product is commutative, so I can write this as v1 dot v1 plus v1 dot v1 dot. So I have flipped this because this is a commutative, and this is nothing but 2 times
v1 dot v1 dot
v1
dot.
dot. So the derivative of some vector dotted with itself is nothing but 2 times the vector and the derivative of that vector. Okay. Let us go to the lecture notes. Okay. So see, we have the derivative of this vector dot with this vector, and this should be equal to 2 times this vector and the derivative of that vector. This is what I have written. 2 times this vector, derivative of that. Is it clear? Is it clear? Are you
Yes, sir.
clear?
Yes, sir. Yes, sir. It is clear, sir.
Okay, so cancel this 2 and 2 will get cancelled. So we have 1 upon m total summation of mi ri dot summation of mi ri double dot. So it is dot here. Okay, so it becomes ri double dot. So 1 by m total summation of mi ri dot dotted with summation of mi ri double dot. Okay, so now we get the expression for this d by dt of this thing, d by dt of this thing is nothing but summation of mi vi m total dotted with summation of mi ri double dot. What is this thing? This is nothing but by definition it is vg.
AG, sir. Sir, VG, sir.
Yeah, again you can go to the definition of the center of mass position rg and differentiate it, you will get this.
VG.
Similarly, dotted with MIRI. RI double dot is nothing but the acceleration of ith particle. So I have written this AI. Okay. So this is VG dot. What is this MIAI? So
F.
it is the net force on the ith particle, which I have written as Fi. Okay. This is Fi, net force on that. It will take internal both as well as the external forces which are acting on this ith particle. So this MIAI is Fi, where this Fi is the total. Now this Fi will have two major components. One is the force acting, internal force acting on the ith particle, that is Fi internal plus Fi external. So taking the summation, giving summation to each of the two components, we can get summation of this thing and summation of, and we know, now we are familiar with this thing, that summation of Fi internal, when we sum up the internal forces throughout the system, it comes out to be 0. So this term vanishes. This term is 0. And the only term remaining is this. So the total external force, the net external force acting on the system of particles, when you dot it with, so I can write it F external, this is the net external force. You sum every external force which is acting on the system. Maybe F1 external is acting on first particle, F2 external. You vector sum those all. You vector sum all those external forces, so you will get net external forces acting on the system. Dot it with the velocity of the center of mass, and this is nothing rate of the change of kinetic energy of the center.
Of mass.
Okay, so this is the expression. So the bigger picture is that you calculate the kinetic energy of the center of mass. So it is nothing but net external force of the net external force on the system times the velocity of the center of mass. Okay, so if the net external force acting on the center of mass is 0, the kinetic energy of the system of the center of mass will not change. Or in
Okay.
other words, the center of mass will move on the with the constant velocity. Vg will remain constant because m total is constant, so Vg will remain. So this we know, I think from the previous lectures, if net external force acting on the system is 0, the acceleration of the center of mass is 0. That means the velocity of the center of mass is constant. Okay. So this was the first expression. Now, second expression is homework for you. So you see the work which I have worked out. you can work out it in different way. This is my I have done this way. You can do some by some other way. Okay, and see, you have to practice this. Unless and until you don't practice, you will not get the feeling what I am trying to say. It will just seem that I am doing some mathematical manipulations and getting the result. These results are very important, and uh, I will suggest that you go back and work out these expressions by yourself. Okay, so I have an homework for you. So show that see, this is not the total kinetic energy. This is just the energy associated with the center of mass, and that is only one part of the total energy. If you go back to this expression, if we go back to this expression, the total energy of the system is the energy associated with the center of mass plus the energy associated with the about the center of mass. Okay, so these are two things. So this is only one of those terms. So if you are differentiating this center of mass energy, you will get this thing. But what if we differentiate the whole kinetic energy? And remember, you were also saying that something should be equal to this. I think you are saying that this is equal to this, but you can verify that this is not equal to this, but this is only equal to this. And when you work out, you will find that the rate of the change of the kinetic energy is Vg dot summation of Fix I external, which is the rate of change of first term of the kinetic energy. And we have worked out that. So this thing we have already worked out. Now the second term in that expression, Ek expression, the second term was something like this: 1 by 2 mi
Vi square.
vi with respect to g. So when you differentiate this thing, you get two terms. One is this and one is this. Okay. So see, this comes out to be Fi internal dot Vi. So there is also the energy associated with the due to the internal forces. So if the particles are interacting with each other, this is the amount of the power. For example, this is the amount of the power they are gaining, or maybe they are losing due to maybe friction or something else. I don't know. Or maybe say the two particles are attracting each other and they are losing the kinetic energy and their potential energy is raising. So I'm not caring about what is going on. But only thing I am stressing is that internal forces also contribute to the kinetic energy of the particles. So if you have Earth here and you have some planet here, sorry, you have some satellite here, and this satellite is being pulled. So when it is being pulled, let's assume that it falls towards the Earth. So it will gain the kinetic energy. So that is due to this. These are not the external forces, these are the internal forces. So there is some power being the kinetic energy will be transferred due to the internal forces. Okay. And this term will not sum to zero. Remember, this is the power or the kinetic energy is not a vector thing. So you cannot expect this term to be equal to zero, summing over all the i's. This is a scalar. You will not be getting this term equal to zero. Maybe sometimes you may get, because it will have positive and negative values, but not always. Okay. Similarly, you have this term Fi external dotted with Vi with respect to G. Okay. So this, according to me, how I am interpreting it, which need not be true. This expression is important. So if you don't have any interpretation, that is not required. You need not have some interpretation for these terms. If you know these terms, you can utilize these terms to get your equations of motional, whatever. But if you have some intuition, that is better. So what I find out is that this is the rotational energy about the center of mass. So let's take an example which will, I think, which will explain this thing. So let's assume that M1 and M2 are two masses of our system, and we are applying a force in this direction F, and we are applying the same force but in opposite direction to M2, which is also equal to M1. M2 and M1 are same, and this F and this F are same. The only difference is that the direction is opposite. Okay, so summation of F is 0. Obviously, if you sum this and this, it will come out to be 0. This term is 0. And Fi internal, there is no internal force. I am saying that this mass and this mass, they have no internal interaction. So there is nothing like this Fi internal. Okay, so this is also 0. Now, but we know if we apply F to this and we apply F to this, these two masses will move and there will be kinetic energy associated with the system. So where from that energy come? That comes from this expression. So we have Fi external dot Vi. So we will dot this with the velocity of this. We will dot this with the velocity of this. That will give us the. So these three terms are very important. If you miss one of them, you will get the wrong answer. Is it clear?
Yes, sir. Yes, sir.
I think it is little bit boring, but it is very
Sir,
important. These are
actually, sir, can you scroll down, sir?
okay.
Uh, when you say that, sir, Vg dot, if we are applying this equation, first term of this equation, we
Yeah.
get zero value, and second we get zero. But if we do not know the third term, that is Fi external dot Vig,
Mhm.
uh, so that the power required to translate the body or to rotate the body is this factor Fi external
Mhm.
dot Vi.
Mhm.
Yes, sir. Well, I understand this term, this concept, that how this is related with the rotational motion of the body about center of mass.
Yeah. So, and also like maybe uh, you may think like if you don't work out these, you may think that there is the energy associated due to the external force, and usually these external forces act on the center of mass, and so we have this expression, and there is the kinetic energy associated due to the internal force, and you have this expression, and you will left out this expression if you do by intuition. Okay, but when you work out this, you will automatically get this term. That is why I'm emphasizing on this term. Okay. And this is the better example, which I think I got this example to explain this thing and hope it serves better. Okay. So now let's move to the Lagrangian method. I think we have 15 minutes. We started at 10:15. So we will end at 11:15. Is it okay?
Okay, sir.
Okay. Okay. So let us go to the Lagrangian. To be more specific, it is Euler-Lagrange method. Okay. So this is Euler. This is pronounced as Euler-Lagrange method. So let's first go to the whiteboard and have some discussion regarding this. So have you heard about Lagrangian method, or have you done anything related it? Or this is the first time you are looking at?
No, sir.
You have
In
not.
in applied mathematics, I have used Lagrange method, Euler method.
Oh, for what? I think in that difference numerical techniques.
Numerical technique, yes, sir.
Oh yeah,
Numerical numerical analysis.
I got it. Yeah, there. So, what is Euler Lagrange method? I will not get into the details, but to get the flavor how this comes. So, this is basically from the variational calculus. Okay, there is a famous uh,
Euler equation.
branch of mathematics which is known as variational calculus. Okay, so what it is basically we have some. Let's say P1 point, okay, and we have some P2 point. So we have these 2 points, P1 and P2. And so we have some integral, okay. We have some integral and we integrate that we take that integral from P1 to P2. P1 to P2. We have some function. Okay, we have some function. For example, let us take this as x and this as y. So we have some function. Uh, let us call this function as f. And we want this function, we want to integrate this function. Okay, from P1 to P2. So we have endpoints that is P1 and P2, and we have some function which we want to integrate. But the thing is that mere integration we are not looking at. We also want to minimize it. We want to minimize this function. So Euler and Lagrange solved this problem using the famous method which is known as the variational calculus. This is not the topic of this course, but I will just share. This is like the minimization problem, and this is what I was trying to make you understand what Lagrange, Euler-Lagrange method is. So it is all about giving the differential equation related to this problem. So this is an integral problem. We will get a differential problem related to this problem. So let us be more specific and uh, let's frame same problem. So let us uh, let's assume we have some particle. We have some particle here, and it want to go there. There may be gravity and other stuff also. So it has to go from this point to this point. So we don't know how it, maybe there is some constant path or something else. So this goes like this. So you, some of you may say why it will go. Maybe this is an electron and there is some electric field also in this direction, which is not constant, which is such that the electron follows this path while going from this to this. So you can get this path using Newton's laws of motion. If you know what is the force acting on this electron, you can generate this path. But there is alternate way of getting this path, which was given by the Lagrange or the Euler and Lagrange. Okay, so how it works? We calculate the Lagrangian. Okay, so what is the Lagrangian? It is nothing but kinetic energy of this particle minus potential energy. Okay, so this is the Lagrangian associated with this particle. So what is the path followed by this followed by this electron or the particle. So Newton says us apply the second law and get the equation of motion or get this path. But what Lagrangian method says is that this electron will follow the path in which this term has minimum activation. That is, if you integrate this term from this point to this point, you should get the minimum value. So for example, you have this path, you have this path, and maybe some this path. So you integrate this term through all the paths, you will get different value. The path
Is that
which will give them, yeah.
is that the electron will traverse that path in which the value of kinetic energy minus potential energy will be minimum.
No, integral of this thing.
Sorry,
Okay.
integral of this. I see.
Integral of kinetic energy minus potential energy. Okay. From P1 to P2. Okay. So
Integral of the
the path which gives us the
value of this.
minimum amount of this thing from this point to this point, that path is the path followed by this electron or the particle. Now, but this integral is not easy to calculate and we don't know what is the path and other things. So
Yes.
we will be using this Lagrangian method. So I know this is the same problem, isn't it?
Mm.
This and this is the same. We have some integral and we want to minimize this integral and using some path. We need to find the path from P1 to P2. But
Yes, sir.
Lagrange says, what are the corresponding differential equations for this minimization problem
Yes, sir.
is like this. So you define Lagrangian as E kinetic minus E potential, and the corresponding equation is delta by delta Q dot. This is very important to because Lagrangian is a very good method and very simple method for complex systems because you will be dealing only in kinetic and potential energy, no vectors there. So this is
Yes.
the power of the Lagrangian method. Okay. So this is the course. So this integral problem has been changed to differential equation by what is the corresponding differential equation? This is the corresponding differential. D by dt of partial derivative of this Lagrangian with respect to the variables. For example, if there is x and y, so del L by sorry
Lex.
partial Lagrangian by partial x dot minus partial Lagrangian by partial x equal to 0. Okay, so
Sir,
we
in
will.
on whole these two terms are only for del z by del q.
Oh, we will take example. I think that will make you more clear. Okay. Yeah. We will take this example, and if still there is doubt, you can ask again. Okay. Hello.
Okay. Okay, yes, sir. Yes.
So this is the pendulum. This is the x-axis, and this is the y-axis. Don't tell me why you are taking this as x and this as y. This is just at that
Yes,
point of time, this come to my mind that I have taken this x and this as y. You can also take this as y. Okay.
no worries, sir.
Yeah. So first we will calculate the Lagrangian. So Lagrangian is Lagrangian for this mass is
Sir, Lagrange for this mass is this, sir? Uh, just you say that, sir, it is integral. Why you are writing ek minus ep?
no. What I am saying, Lagrangian is this thing. Okay.
Integral of this.
No,
Integral
no,
of
no. No. See, Lagrangian is just this kinetic.
Energy,
Sorry,
force energy.
just a minute. Yeah, see. Yeah, what you were asking?
I was asking, sir, is L integral of this or only the difference between Ki and Pi?
L is just a difference between K kinetic energy and potential energy.
Yes.
And what Tyler Lagrange says is that the particle will follow the
Okay.
path in
Now
which
I'm
this integral is minimum,
yes.
which gives
Is
the
minimum.
minimum value to this integral.
Yes. Okay.
And the variational calculus, when we use the variational calculus, we find that saying
Integral.
this thing, minimize this integral is equivalent of saying d by dt of this thing minus this equal to 0. These are same.
Okay, sir.
Okay, if you will solve this and solve this, you will get the same answer.
Yes, sir.
Variational calculus is very powerful technique. Uh, yeah, when you go for the optimization, you can also maybe in MTech you will get this course. I think we had done this course in MTech in NIT Sydney. So it is a very good and powerful technique. We also use this technique in this strength of materials. Okay, where you have beams. So you will be learning this thing in your higher classes. Okay.
Okay,
So
sir.
we have this Lagrangian equal to E kinetic minus E potential, and E kinetic is nothing but 1/2 of m E dot V, and V is nothing but x dot I plus y dot j, isn't it? And similarly, this thing, you make the dot product, and this will give x dot square plus y dot square. I hope this is clear.
Yes, sir. Yes, sir.
Similarly, E potential, potential energy of this mass. If we take the potential energy of this level equal to 0, then potential energy of I think we should continue from. I will continue this lecture from next class. Uh, Time has also, like, I think 1 hour has gone.
Yes, sir.
Okay, so we can end it because I'm not feeling
Well,
comfortable. We can continue from next class. Any question?
no, not yet, sir. Okay,
Okay, so we will stop recording.